Well, what information do we have here? We're given the half-life. So T1 half is 2.86 years. And then we have masses. That half-life, the integrated rate law for this showed us number of nuclides present now divided by number of nuclides originally present. So it was a ratio. So these masses are not the number of nuclides, but they are directly proportional to the number of nuclides. So we don't have to convert them to number of nuclides. We can use grams or milligrams. So we'll just say that N of T, N sub T is the 0.100 milligrams. And what was the initial? 1.35 milligrams. So the natural log of NT over N0 was equal to negative K times the time. But we didn't get the rate constant. Can we calculate the rate constant from the half-life? Yeah, we can. T1 half equals 0.693 over the rate constant. Or we can rearrange that. And the rate constant equals 0.693 over T1 half. So 2.86 years. Different units of time can be used here. You just need to keep track of them and make sure that your answer matches the answer requested in terms of units, right? If it gives an answer in seconds and you're answering in years, it's not going to be good. So 0.693 divided by 2.86. So 0.24231. It's always a good idea to keep a couple extra digits. So we're going to have the natural log of the amount currently, or at the time, at the end, divided by the amount initially present. And you'll see that the milligrams cancel out. And this is going to equal negative 0.24231 times time. That's how much time it takes for that to happen. So when I solve that, I'm getting T is equal to 10.7. And the unit on the time here will be the same as the unit on the half-life. So 10.7 years. And then always ask yourself, does this make sense? Is it, ballpark correct? Yeah, because you started with 1.35, and after 2.86 years, it's going to go down to, like 0.65 or something, right? And then another 2.86. And so, yeah, this is reasonable. Any questions? Yeah.
Could we use this information here to maybe calculate how many particles have been ejected given this time? And
Yes.
like from the equation?
Yes, because if you know the number of particles that you started with and the number that remain, you can find out how many decayed. Yeah.
So do the nuclear equations also kind associate themselves with stoichiometric rules too? Like the ratios and conversion between?
No. No, because there are some decay events that may give out more than one particle, right? But it's still, we're looking at a single decay event. So if you were trying to look at number of radioactive particles that were given off, I suppose you would look at the stoichiometry. Yeah.
Thank you.
Any other questions?
If it decayed to a different element, you'd have to convert or never mind, it's not.
So we will have problems like that.
Okay, I was thinking.
Yeah. So here what we're talking about is we're talking about the amount of Pu-236 that remains. And so yes, the stuff that decayed turned into other elements, and we're not going to worry about them, right? But if we wanted to calculate the mass of what was left, then we would have to consider that. Any other questions? Yeah, so we already did this shortcut in the previous problem. Mass is directly proportional to number of nuclei, and we're looking at the ratios, so we can use final and initial masses instead of the numbers. The rate of decay is also directly proportional to the nuclei, number of nuclei, and so you can also look at the natural log of the rate at time t over the initial rate. So radiocarbon dating, you may have heard of this. This is a radiometric dating technique. It uses the predictable decay of radioactive isotopes in the environment to estimate how old something is. We can do this with formerly living organisms. We can also do this with rocks. There are different types of isotopes that are used for different processes. So radiocarbon dating was developed in 1949 by William Libby. And this makes use of what's called a radioactive signature that results from the presence of carbon-14 in the environment. And he got the Nobel Prize in 1960 for this. And this technique is used by people who are interested in how old things are, right? Archaeologists, geologists, anthropologists, and other scientists. So an example of the use of this is the Dead Sea Scrolls. So these ancient-looking scrolls were found stuffed in jars in a cave. And they were able to determine the approximate age of the scrolls using radiocarbon dating. And so these were 1,000 years older than any known manuscripts of the Hebrew Bible. So it was pretty cool. So how does this work? Carbon-14 is always being formed in the upper atmosphere. So there's a lot of radiation and stuff coming from the sun and outer space, mostly from the sun. And so we've got neutrons showering down, right? They don't get all the way to Earth because we have our layer of protective gases. But this is one of the things that stops those neutrons. The nitrogen is bombarded and gets converted to carbon-14 and a hydrogen atom. And then the carbon-14 decays back to nitrogen by beta emission, and it has a half-life of 5,730 years. Now, in the textbook, they changed that number between two editions, and so go with whatever the book says or with whatever Mastering Chemistry says. Because I think sometimes it says 5,735. So because carbon-14 is constantly being formed and constantly decaying, the equilibrium concentration of it in the atmosphere is fairly constant. Right? And so atmospheric carbon-14, along with regular carbon-12, gets oxidized to carbon dioxide, gets incorporated into plants through photosynthesis, and makes its way up the food chain. So living organisms, currently living organisms, will have the same ratio of carbon-14 to carbon-12 as what is found in the atmosphere. So we all have carbon-14 in our bodies. Any carbon source, any carbon sample anywhere is going to have carbon-14 in it. When an organism dies, it stops taking in more carbon-14. The carbon-14 that was present at the point of death is still there, but it's decaying, right? And so we can measure how much carbon-14 is left relative to the carbon-12. And, you know, if this ratio is half, oh, see here, here's the different number, 5,715 years. I gotta fix that. So after 5,715 years, the ratio of carbon-14 to carbon-12 is going to be half what is present in the atmosphere. Does that make sense? So you can only go so far back because the amount of carbon-14 in the atmosphere is very small, right? And so whatever's in an organism is going to be small. And it cuts in half and cuts in half and cuts in half. And eventually, that level of carbon-14 becomes too small to measure accurately. And so you can get to about 50,000 years. And older than that, not helpful. I can tell you it's over 50,000 years old. So they can check the accuracy of this by looking at objects whose age is known through historical sources, right? It's recorded in history that this person died in this year, right? Well, you could sample what's left of them and see if that matches up with what's predicted. There are some variations in the carbon-14 content. And so corrections can be made using data from western bristlecone pine trees. That's remarkably specific, isn't it? What? I think there's a slide about that. No, there isn't. These trees live for a really long time, right? And so you can look at the different rings in their trunk, and that's related to the amount of carbon-14. Okay. Researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. A measure of its carbon-14 decay gives a value that is 89% of that found in living organisms. How old is the scroll, and could it be authentic? So this is how the result of carbon-14 testing is usually given as a percentage, because it's the ratio of how much is left. Well, I'm sorry. This always makes my head hurt. So 89% would tell us that we have left 89 out of an original 100. No? Oh, your answer. I'm like, I thought you were... I'm like, oh, it was very daring. So the ratio... The ratio of NT to N0 would be 89 over 100, 89%. So 500 BC would be how many years ago? Let's call it 2020, so 2,520, right? Is what they're claiming. How does that relate to a half-life?
Half-life of carbon is like 5,000.
It's 5,715 or 30, depending on which slide you look at. Is that right?
Oh, yeah.
Okay. So this is, we would expect 50% in this many years, right? So it's like, well, maybe we do have to calculate it. So the natural log of 0.89 is going to equal negative k times the age. This is the half-life. So the rate constant is equal to 0.693 divided by the half-life. So 1.21 times 10 to the minus 4. And we come up with T is equal to 963 years, which falls a wee bit short of 2,520.
No.
The answer is no. It could not be authentic. How old is it? 963 years old. That's not a super precise number, but when you're measuring things that are that old, you know, you're not looking for the exact minute that it died. Right? So, as far as I know, radiocarbon age cannot be faked. You know, you can take papyrus and make it look old, right? You can use the same kind of ink that they use, right? You can do all these things to make it appear older than it actually is. But you can't fake the ratio of carbon-14 to carbon-12. Another type of dating is called uranium-lead dating. So radiocarbon dating, the object had to have been alive, taking in carbon. So what if you've got like a rock that wasn't alive? Or if you've got something that's more than 50,000 years old? We can look at the ratio of uranium-238 to lead-206. So this will give us a measure of the time that has elapsed since the rock solidified. Because whatever uranium-238 was initially present will continue to decay and form lead-206, which is still in the rock, right? Because it went through that whole series of decay steps, and it stops at lead-206. So the half-life for that is 4.5 times 10 to the 9th years. Significantly longer than carbon-14. So what if you have lead that was originally present in your rock? Well, that's going to have a different composition of isotopes than what you get from the decay. So the stuff you get from the decay is only 206. So a rock contains a Pb206 to uranium-238 mass ratio of 0.145 to 1, assuming that the rock did not contain any lead-206 at the time of its formation. Determine its age. So we need this half-life 4.5 times 10 to the 9th. Was it 5? 4.5? See, I look at it and I forget it immediately. Now, this is a little trickier because this ratio is how much lead-206 is currently here divided by the 238, the uranium that was originally present. And this is the issue that Scott anticipated, right? The mass of lead-206 present now is not the same as the mass of uranium-238 that was originally present. So we have to convert it somehow, or go to number of isotopes. But it turns out we don't have to go that far. So let's use this ratio and say we have 0.145 grams of lead-206. And we have 1.00 grams of uranium-238. We want to know what mass of uranium-238 made this mass of lead-206. So one uranium atom will decay through those steps and form one lead atom. So 0.145 grams of lead-206. And we want to convert this to uranium-238. And so we've got lead-206 down here. Where are we going to get our masses? That's where we've always gotten them, the periodic table. Well, they are sort of on the periodic table. The problem is that the masses on the periodic table, like lead 207.2, that's the mass of the average atom, right? We want the mass of this particular one, which is its mass number. So we're going to have 238 grams of uranium-238 for every 206 grams of lead-206. So this corresponds to 0.167, probably over here. I'll just forget that. 1675 grams of uranium-238. So we're using our integrated first order rate law, and I'm just gonna call it N. What does this mass of uranium represent? Does this represent the amount present at time t? No. Does it represent the amount initially present? No. This represents the amount that decayed. Right? So if we started with 1 gram, then this much went away. So this is going to be N0, and N sub t is going to equal 1.00 grams minus 0.1675 grams. Or 0.832. So again, you know, they give us the half-life, we need the rate constant. 0.693 divided by the half-life. So 1.54 times 10 to the minus 10. So the natural log of 0.832 grams over 1 gram is equal to negative 1.54, ran out of room. Times 10 to the minus 10th times t. Ooh, that's a big one. So t equals 1.19, just kind of guessing there, let's take phase. So 1.2 times 10 to the 9th years. That's an old rock. Any questions? You need to understand what the equation is and what the numbers are so that you can think about this correctly. This is a type of problem that's really hard to just put into a formula. Oh, I do this and this and this and I get my answer. Because we know that students like to do that, and so we'll ask the question in different ways to mess you up, to see if you actually know what you're doing. So, the age of the Earth. So people have been measuring the ages of rocks on Earth. And rocks that are over 3.5 billion years old have been found on every continent. The oldest ones are about 4 billion years old. So if we assume that the Earth must be at least as old as its rocks, then, 4 billion years old. There are meteorites that have struck Earth that are 4.5 billion years old. Those would have been formed at the same time as our solar system, and so the best estimate is 4.5 billion years. The universe is estimated to be 13.7 billion years old. These are estimates.
People hurt my head. Why, who said the universe is 13.7 billion years old?
Well, that's beyond the scope of this class.
No.